Hi, welcome back from summer. We are doing limits. It says in one day, but we're really going to do limits in about 20 minutes, hopefully. Okay, concept of limits. We've lived with the concept of limits even before we got to calculus. For example, we're looking at this graph that says average male height from the United States, and we could find it interesting, what a data point would be, let's say in the 1930s or 1940s. That would be interesting, but what's most interesting, right, is the trend, and that there appears to be a limit involved here as the years increase. And so this is similar to what we've done in calculus with looking at the limit of a function as x approaches infinity, just looking for possible horizontal asymptotes, like is there a limit? So we're used to this idea of limits. And there's another way that limits are applied. Instead of x approaching infinity, we could imagine x approaching 0 in cases where x isn't allowed to be 0, but x can certainly get super, super close. And so we'll go into this a little bit more in a little bit more detail when we do derivatives. But this concept of limits can take a pre-calc formula of the slope of a secant line and then make that distance between those 2 points, between the x and the x plus delta x, become smaller and smaller and smaller until we actually get the slope of the tangent line. And so once again, we'll talk about that more later. Another way that limits is applied, let's say that we're looking at this first picture here and we're trying to approximate the area under the curve, and instead of, we don't have an area formula for this crazy looking shape, and so we're like, oh, you know what, let's just stick a rectangle underneath there and let's approximate the area. Obviously we're going to be way off, but wonder if we increase the amount of rectangles. Instead of 1, let's use 4, and we can see that in the second picture that 4 rectangles, wow, we're going to get a much more accurate approximation. But wonder, instead of using 4 rectangles, we used 8, and we're like, oh, that's even better, right? And so you see where this is going. What if we used 100? What if we used 1,000? What if we used 1,000,000? What if we used just an infinite amount of rectangles? We're actually going to not just approach the area of the curve, we're going to have the exact value of the area under the curve, and that's integrating, which we'll see in chapter 4. And so basically, if you haven't heard it yet, calculus is a limit machine. It takes pre-calculus formulas, applies this concept of limit to create new calculus formulas. And so let's just kind of go back to what we started with, or you started with when you took honors pre-calc last year and you started limits. You focused graphically, right? And so with this, we know that the limit as we're approaching 0 of this function is 1, right? From the left, it's approaching 1. From the right, it's approaching 1. And let's go ahead and compare and contrast that to the actual value at 0. So when x is equal to 0, y is undefined. So f of 0 is undefined. Just comparing those two, obviously there's still a limit, but the value for y, the value for the function, is undefined when x is equal to 0. And so let's see, I'm just going to double check that we are going, and we are going. Okay. Worst nightmare, right? I make through the whole video and it was never recording. So here we go. Let's look at this graph, piecewise function, and let's look at what's happening as x is approaching -5, right? From the left, the limit's approaching 3. From the right, it's approaching 4. And so we're going to say that the limit doesn't exist. It's approaching 2 different values from the left and from the right. Same thing with, not same thing for -4. With -4 from the left, we're approaching -4. And I'm sorry, we're approaching 2. And from the right, we're also approaching 2. I know it's like 2.1 or 2.1 something. We're just going to say 2. The limit of this function is x approaching -2. Once again, the values coming from the left and coming from the right are different, so the limit doesn't exist. And then one last time, when we're looking at x is equal as the limit of the function is x is approaching 5, it is equal to 2. And yes, that's a sharp turn there, and you may be going, wait a second, is there a limit? There's a limit, there's just not a derivative, but there is a limit there, and it is 2. Okay, so what's going on here? We've got some oscillating going on, right? We're looking at sine of 1 over x, and it really can't make up its mind. It's bouncing back and forth between 1 and -1, and it will do that for all infinity. I mean, all time. They will, for the rest of its life, that's what it will be doing. And so obviously there's not going to be a function there. I'm sorry, there's not going to be a limit there. You'll have to excuse me, I'm coming off of summer as well, so I've got to try to get back into the math groove and using the words. So give me some grace a little bit throughout this video. So anyways, the limit does not exist because it's oscillating. It can't settle in on something. And I want to compare that to something that you probably saw last year. And this function, y equals x squared of cosine of 1 over x, it's different, right? It is going back and forth, but you can see that the oscillating is going from, an even lower point each time, and a little, the height is getting lower, and the bottom, the max is getting lower, the min's getting higher, and it's meeting. And in fact, what you see here is you see it being squeezed from the function y equals x squared from above, and the function y equals negative x squared from below. And that's actually called the squeeze theorem, where you can find the limit that way. Since the limit of x squared is x approaching 0 is 0, it's the same thing with negative x squared, and it squeezes it, then also this has a limit. But once again, not the same thing as oscillating. I wanted to compare and contrast those two. Okay, so the limit of this function is x is approaching 1. From the right, we're shooting up to positive infinity. From the left, negative infinity. And so obviously, the limit does not exist. And there are 3 ways that limits can fail to exist, and we just talked about them, right? Approaching 2 different values from either the left and the right side. Either we're going up to positive infinity on both sides, or negative infinity, or both negative and positive infinity, or it's oscillating. Those are 3 ways. Okay, then last year you learned about finding limits numerically, and that's with the table. And you're like, why would we ever do that? So true, right? And even this example right here, the limit of x squared minus 5x plus 2 is x is approaching 2. We just do direct substitution, right? We plug that 2 in, we get negative 4. So why would we be making a table? In this case, we're using it because it's easy to see, to understand how to even set up a table. So if we're approaching 2, and we want to approach, and let me get a pencil here so you can actually see me. I don't know if you can just see the cursor going back and forth. If we want to approach 2 from the left, right, we don't want to, here's 2 right here. We don't want to, let's say, start with 1 and then go 1 1/4, 1 1/2, 1 3/4, here I come. Okay, now we got to start closer than that. We've got to start at 1.9 and then get really super close. I mean, 1.9, we're right in the face of 2, but even closer, 1.99, 1.999. Same thing coming from the right. We don't want to start at 3. We want to start at 2.1 and get closer and closer in so we can understand what's happening. And so obviously we're finding the limit numerically. We get the same thing as finding the limit using direct substitution, which is analytically, and that is as it should be. So why do we do tables? Let's look at another example where we've got the limit of x plus 4 over x squared minus 16. So we have a rational function, and I know what you're thinking. You're like, that's overbait. Let's just go ahead and factor out that's the difference of 2 squares. We could do x plus 4 times x minus 4, and the x plus 4s can cancel out. And you're like, oh yeah. And then we're left with 1 over x minus 4. We can't do direct substitution, right? So we really don't know exactly what's going on here. And so a table is, or finding the limit numerically is the way to go. And so once again, we'd approach 4 from the right, from the left, pick up our calculator and see, oh, this is why the limit doesn't exist, right? We have a vertical asymptote. And then from the left, it's going to negative infinity. The right is going to positive infinity. I realize I'm talking fast because I also realize that there are going to be some of you that don't need this review at all, and I'm requiring it. So even speed me up more. I'm not going to, well, I'm not going to know you're doing it, but I'm going to be okay if you want to speed it up. At the same time, if you're like, whoa, I had the best summer ever, and I don't remember anything, or I remember very little, and you're taking BC, slow it down, take good notes. We use this, the first 4 classes, 4 or 5 classes or so, to get back into the groove of the first 2 chapters. We try to do it with as little stress as possible. So slow it down if you need to, pause, take notes. But if you remember all this, speed it up. I'm fine with that. All right. All right, now we're looking at this function, and obviously we want to solve it analytically, which means just use algebra. So we would go ahead and factor, right? And then once we get rid of the denominator, we can go ahead and use direct substitution. There is another way to do this, and I'm not sure if you learned it last year or not. So let's just start talking about it now. If we did do direct substitution, if we plugged 5 into the original one, we'd get what? In the numerator, we'd get 25 plus 5 minus 30, so that's 0. And the denominator, we'd also get 0. So that's what we call an indeterminate form, 0 over 0. And so there's a lot of other indeterminate forms. We could have a negative infinity over negative infinity, positive infinity over, all those. We could have infinity times the infinity, 0 times infinity, 0 to the 0, 1 to infinity, and infinity to the 0 power. And when we see this, and when we see that we have an indeterminate form, we know that in some cases we can use L'Hopital's rule to help us find the limit. So if you didn't learn about L'Hopital's rule, you're going to learn about it now, which basically you can only use it if you have an indeterminate form. I usually have just used it when we have the first two indeterminate forms, 0 over 0, infinity over infinity. And so what you do is you take the derivative. And once again, we haven't done our derivative review, but I know you remember the power rule, which is just if we took the derivative of the numerator, we get what? 2x plus 1, right? And the derivative of the denominator is just going to be 1. So 2x plus 1, we do direct substitution, we get 11. That's the L'Hopital's rule, where you take the derivative of the numerator, take the derivative of the denominator, and if you can use direct substitution, you go ahead and do it. Sometimes we have to take the derivative a second time, and then go ahead and do direct substitution after that. We'll talk about that more in class if you have questions. All right, so here we've got another limit we can't factor. We could use L'Hopital's, but let's go ahead and talk about what we could do. Do you see the numerator as a binomial? Anytime I see a binomial, I think about multiplying it by its conjugate, because if we multiply a binomial by a conjugate when it's part of a fraction, that really does kind of mix things up and maybe make things happen. And so this is the work. Once again, you can slow it down, you can pause it, see the work, but this is the work of just multiplying numerator and denominator by the conjugate. And I don't know if you've noticed, but when you multiply the conjugate, note when we're going from, once again, I don't know if you can see my cursor and where it's moving, so let me just get some. When we're moving from the first step to the second step, note that they actually multiplied the numerator out, but they left the denominator like this, and we always want to do that. It's not going to help us if we start distributing and expanding the denominator. Leave the denominator the same. Could we use L'Hopital's? Absolutely we could. So you can have fun and pause and take the derivative of the numerator, take the derivative of the denominator. You're going to get the same answer when you do direct substitution after that. All right, two special trig limits. Yes, you need to have these memorized. Sine x over x, the limit of sine x over x as x approaches 0 is 1, and the limit of 1 minus cosine x over x as x approaches 0 is 0. And the way I remember that is I see sine has a 1 hidden in there. Look, wasn't that nice, the 1 and the 1? And cosine has the 0 in there. So that's how I remember which one's which. And you know what? That's important. I mean, you could call it a cheat, but I think it's important to find quirky ways to remember things, because this course has a lot of things to remember. So we got to start now committing things to memory, just like I like to, and you're going to hear me talk about this in class too. I think a good analogy is thinking about med school and having to take anatomy and physiology 1 and A&P 2, and memorizing. You have to memorize the body. You can't just be like, I'm going to memorize it for a test and I'm going to move on. So same thing here. Everything really does build, but you know that by now. So just pause this. You can look at using some identities, some trig identities, right? And then rearranging things so we could actually use the sine x over x. And note that when we're taking the limit of something times something, I think this is important to notice right here, we're really doing two limit problems. We're taking the limit of sine x over x as x approaches 0, which gives us the 1. And then we're doing the limit separately of sine x over cosine squared x, which we can use direct substitution, right? All right. All right, you know what? I am sitting here doing this writing on my, you don't know this, on my computer. I just need to turn around and actually do this on the smartboard. Oh, I really hope that I'm aligned. Let's find out. I want to talk about when we're looking at, oh, that's Thank goodness, because I did not align it since I left the end of the school year. So let's go. I want to make sure everyone's okay, like you realize that is the same thing as that, but obviously this is the one thing that doesn't belong, right? Because this is the angle being squared, this is the function being squared, this is the function being squared. All right, so just, you know, just a nice little, hey, we're coming back from summer, let's make sure we remember math. Here we're looking at limit with an absolute value, and so we can't do this. We can't do it with any of the methods that we've done so far. Yes, if you plug 0 in, it is going to be an indeterminate form, but we can't do derivatives with absolute value. We actually have to split the absolute value up into when x is positive and when x is negative. So you can use L'Hopital's on this, but you'd have to do what we're doing here already, which is look at what's happening to the right and what's happening to the left. So we could go ahead and plug things in, right? We could, as x is approaching 0 from the right, we're plugging in positive numbers, and we get 2, and as x is approaching 0 from the left, we plug in negative numbers, and we're going to get -2, and this is the graph, what it looks like. So obviously, approaching 2 different values, the limit does not exist. It'd be fun to use L'Hopital's here. All you would have to do is, let me get back. Let me pick up a darn thing. If x is approaching 0 from the positive, we're looking at positive, then we don't need the absolute value, right? So that's the same thing as this. And obviously, you don't even need to L'Hopital's because you would just bloop like that, right? So you could take the derivative, but you don't need to. And here, if x is approaching from the left negative, then we know 2x is going to be negative, right? And so we could just go ahead and cancel and get the -2, or do L'Hopital's. See how many times I can say L'Hopital's in this video. All right. Once again, I know I'm going fast. Slow me down if you need to, or speed me up even faster. So here's something that's important when we're talking about left-sided and right-sided limits, one-sided limits. If the limit of the function is the same coming from the right as it is from the left, then we know the limit exists at that function as x is approaching c. Makes sense, right? So these are all things that we have committed to memory and we've used and we're good. Continuity is super, super important. Continuity, the way we define continuity is weird because we're really defining continuity at a point, at a single point, which is crazy because I think of continuity like you do. It's like continuous, like the road is continuous. It's continuous. Oh no, there's a big pothole. Okay. That's discontinuity. But to talk about continuity at a point, which is what we do, is a little bit weird. But let's just do it anyways. At a point C, so that means just, just any x we're looking at, we have to have a value for y. So f of c has to exist. There has to be a value there. When x is c, y has to equal something. And we also have to have a limit there at that point. And then those two values have to be the same. And if all those three things happen, then we say we have continuity at that point. And then if we're looking at a function over an interval, and we have continuity at every single point, then we say it's continuous everywhere. And so once again, I remember I'm sure that you saw these last year at the end of honors pre-calc. But like, for example, case 1, c doesn't even have a value there. That open circle means it's undefined. There's no value for y when x is equal to c. So you're not continuous. The second one, we've got that open circle, but that's okay because we've got the closed circle. And the closed circle is telling us that we have a value. We have a value for y when x is equal to c, but darn it, there's no limit. So not continuous. Same thing here, well, a little bit different here. We have a limit, right? Coming from left, coming from the right. This value, whatever that is the limit. But it's not the same thing as the value of the function at c. So that's why these are not continuous. Let's see what remember. Oh, okay. Yes, remember that. Super important to be able to understand what continuous means. So here's a piecewise function. Determine if this piecewise function is continuous at x equals 1 by using the 3 conditions. And so basically what we're looking for, right? I'm not going to repeat the 3 conditions. We just talked about them. So there's three ways we can do it. You can use a table, we can use a graph, and we can use a shortcut. So let's see what the table and the graph looks like. It's just making a graph and realizing, looking at this one right here, I put those dots around it because obviously for the second part, x cannot equal 1, but we have to have a placeholder, right? Because x can't equal 1, but x can equal 1.00000000001. So we can't just start with 2, right? We got to start with 1. That's going to be where our open circle is right here. And so we can see from our table that, oops, we plug in 1 and we get 3, we plug in 1 and we get 4, or we could see from our graph that the limit doesn't exist. And what's the shortcut? Just plug it in. So if you understand all this, then we don't have to go through it each time. It's just plugging in. You plug in 1 for this and you have a 3. You plug in 1 in here, you have a 4. They're not equal to each other. There you go. You don't have continuity here. Okay, so if you have a discontinuity, you're either going to have one that's called removable or non-removable. And so the removable ones are going to be anytime you have that open circle, right? And think about how you even got those open circles. You got them from taking a rational function and factoring and canceling out something like, x plus 4 or x minus 4 in the denominator. So the problem went away. You still have a limit, but you don't have a value there at that function. That's removable. But if you're dealing with a rational function where the x minus 4 doesn't cancel out in the denominator, you're stuck with the vertical asymptote. And you can't remove that vertical asymptote. I kind of think, little circles. It's easy. You just fill that in. You remove that little circle. You just can't really remove that asymptote. I think that's kind of a common sense way to look at it. To understand removable and non-removable. So this says find all discontinuities and label them as removable or non-removable. So what are we going to do? We're going to factor, and when we factor, we see that the x minus 3's cancel out. So at x equals 3, we would say we have a removable discontinuity. And at x equals negative 4, we have a non-removable discontinuity. So just to remember, the problem is when either of these binomials would be 0, right? So the problem would be when x plus 4 is equal to 0. So that means we'd have an issue at x equals negative 4. And the problem would be if x minus 3 is equal to 0, right? So this is the one that's removable. The x is equal to negative 4. We'd have a non-removable because we'd have a vertical asymptote. Okay, now we're looking at another rational function. So remember, rational numbers are numbers that can be expressed as a fraction. And so when we're looking at rational functions, we've got an x in the denominator. And so if we think back to honors algebra 2 trig, we learned rules, right? We said, oh, okay, if we're dealing with a rational function and the highest numerator in the, that wasn't nice, the highest numerator in the, okay, totally not aligned, but that's okay. The highest numerator in the, the highest power in the numerator is 2, and the highest power in the denominator is 2, and they're the same, then we know that the ratio of the leading coefficients is going to be where our horizontal asymptote is. And you're like, Ms. Overby, they're not asking for horizontal asymptotes. They're asking you to find the limit of this as x approaches infinity, which is the same thing, right? It's the same thing. But in calculus, as you learned at the end of honors pre-calc last year, we have the actual way of finding why there's a horizontal asymptote at y equals 3/2. And so what we do, our method is we take the the highest power in the denominator, which is x squared, and we divide every single term by x squared. And that's legal. It doesn't change the value of this function at all. We divide every single every single term by x squared. We simplify, and we end up with this right here. And so what we've got to do now is find the limit. And remember how I told you we can break up our limit. So we can find the limit first of 3. So the limit of 3 is x approaches infinity. Always kind of sounds funny, like 3. Okay, 3 is just going to be 3 no matter what. And we have to remember these are functions. So what is 3? 3 is y equals 3, right? And if we graphed it, be like that. So obviously, as x approaches infinity, we're still going to be 3, okay? So the limit of 3 is 3. That's how we get that. Let's talk about the limit of, so we're looking at the limit of 4 over x squared. I like to think of it as pizza. We have 4 pieces of pizza, and there's 4 of us. Woo! I'm sorry, not 4 pieces, 4 pizza pies. All right, so 4 pizzas. And so there's 4 of us. We each get our very own big pizza. Let's say there's 8 of us. So we'd have 4 divided by 8. That means we each get a half pizza, which that's not bad. Okay, now there's 40 of us. Sorry, a big group, big party. We only have 4 pizzas. And so 4 divided by 40, that means we're all getting 1/10 of a slice, or 1/10. Our slice is going to be 1/10 of a full pizza. Okay, that's a little appetizer maybe. Wonder if there's 400 of us. Word got out. There's really super big party. Now we're getting, each of us get a slice that is 1/100th of a complete full pizza. You know, our slices are getting smaller. So when we have 4 in the numerator and our denominator is going to infinity, just think about 4 pizza pies and being divided by 1 million people, right? Our pieces are approaching like, you know, microscopic size, right? And soon they're approaching 0. So pizza or no pizza, however you want to think about that, anytime you see a constant in the numerator and the denominator shooting off to infinity, that means we are approaching 0. The limit is 0. So here, the limit of 2 as x is approaching infinity is 2. The limit of 1 over x squared as the limit is approaching, or as the limit of 1 over x squared as x approaching infinity is 0. So there we go. We get our 3/2, which is also where our horizontal asymptote is, right? Right there at 1.5. And so the limits, infinite limits, I'm sorry, limits at infinity are the same thing as finding horizontal asymptotes. All right. Whew, we're going through chapter 1, and I don't know, how many minutes has it been so far? Because I was hoping to keep this to 20. We're at 27. Yep, it's a long one. All right, here we've got 3 minus 2x over 3x to the third minus 1. Bottom heavy, that's the way I like to look at it. X is raised to the third power in the denominator. It has a higher exponent value. And so we're going to do the same method. We're going to divide every term by x cubed. It's going to simplify. We're going to find the limit. And yes, our limit's equal to 0. And we knew from it was going to turn out that way because from Honors Algebra 2 Trig, there's a horizontal asymptote at 0. Okay, this one is, whoops. This one is square root. Square root of x squared can be equal to x, but it could also equal to negative x. And in this case, since we're actually looking at x as we're approaching negative infinity, it is going to equal, the square root of x squared is going to equal negative x, right? So let me see what I've got here. Let me get rid of all of this. So it makes sense, right? If let's say that let x equals -4, like we said here, then x squared would be 16, right? And then the square root of 16 would be 4. But we know that x is equal to -4, not 4. So when we looked at these, we would go through and we would we'd put that negative there because if we don't, we're going to get the wrong answer, right? If x is approaching negative infinity, x cannot be positive. And so, all right, let me go back over to my computer. Okay, so we're going to scroll down. Hope that makes sense. If not, you can always ask me in class. But we're doing the same technique. It just looks a little bit different because of that negative being involved. Note too down here that we really just are doing the limit of this as we look at each of our terms underneath the square root. All right. I hope that we're being close to being done. I did not want this to be 30 minutes. All right, intermediate value theorem. These existence theorems are important. You're going to see more of these as we work together. I believe in chapter 3 we'll add to these. So intermediate value theorem is really basic, right? It's just looking at a function over an interval from a to b. So if we're looking at the x values from a to b, then that would make sense that the y values would be from f of a, the value of the function at a, to f of b, the value of the function at b. And so the intermediate value theorem says, first and foremost, this part of the function over this interval has to be continuous. Otherwise, it's not going to work. It has to be continuous. And that we have this y value, w in this case. They use different, this isn't, I mean, they use different letters in different examples. But in this case, we're just using w, that there's this y value that's between f of a and f of b. And the intermediate value theorem guarantees that there's an x value between a and b that gives us the y value of w. So pause that. I think with the theorems, what the best thing to do is pause it and explain it to somebody else. And if you're by yourself, just explain it to yourself. We'll be working with these during class. The theorems are important to, well, for the AP exam. They're just important to calculus. All right, and then this last thing, sketch the graph with the following characteristics. You know what, be my guest, have fun, do this. I'm not doing it. It's too long already. And if we wanted to try to do this together in class, we could. Have fun. And we are going to do Delta Math number 1 in class. So thanks for joining me. I did not want it to be this long, but all right, 31 minutes. We did it. All right, see you in class.